Hi, long time no see, right? So this video is about damping by frictional force in harmonic motion. So I guess you are familiar with the kind of motion in which the oscillation is damped by viscous force, and that too linear viscous force. We don't consider those quadratic terms or higher order terms, but still, I think we are familiar with it, and something which is new and something which is out of ordinary can be said as extraordinary is when it is done by a constant force. It has various interesting properties, and I will be talking about two of those, one of them being its time period. Other one is about its motion itself. So it has a peculiar kind of motion, but it is a nice thing, and I mean mathematically it turns out to be a different situation altogether. Let me show what I mean. Okay, so let me change the color. Yep, yep. So suppose that I have um, x-axis and this is y-axis. So let me write that. uh, this is x-axis, this is y-axis, and this is the particle that I have under consideration, or subject I mean. uh, yeah, that this is the assumed origin, I mean assumed center for the central forces, where the central force is defined as minus kx. So a general spring kind of force, which is necessary for SHM. And uh, suppose we like, so suppose the starting point of the block is right here, which is x naught, just suppose. And also suppose that there is a spring attached to it, so as to like see actually this force working. And once we leave it there, it will have two kind of forces, right? One is this force which is due to the spring. So I can write that as acceleration, which will be negative, is equal to minus kx plus f, because friction will act in this direction, right? I'm assuming this as friction. And so yeah, mm, we have this, right? What I can do is I can write, since f is a positive quantity, I will be assuming, yeah, let me write it first. So f is equal to k. I have used x not there, I will use x1 here. I can safely assume this, right? This is nowhere near being wrong. I mean, there should be some value of x1 for this to occur. And now I'm going to put this in this equation. What I end up getting is a is equal to minus k x minus x1. You can do the opening thing and you can check that this is like fully equivalent. But I will leave that up to you. If you want, you can do that. I mean, it is also visible. Let's not talk about it much. Yeah. What does this mean? This mean a significant chunk of things. Uh, Let me show what it means. Okay. So for the starting point, we can say that it is x naught. I mean, this is x naught. I mean, we can say that for the starting point. Starting point. Yeah. So also, uh, it depends, right? If the force is larger than kx naught, I mean if the friction is larger than kx naught, then I mean the maximum friction is greater than the kx naught, then the block will not move at all. So another condition should be put, that f is less than kx naught, which implies kx is less than kx1 is less than kx naught, which implies x1 is less than x naught, uh, in mod to say. So obviously x1 will be somewhere around here, so this should be x1. We can say that. And what does this equation say, our star equation? It says that the particle actually performs SHM about this. So now it is, now x1 is reassigned as the origin if there is a force, and now it does a SSM with respect to that. So yeah, if you bring out the equation, it will turn out to be exactly the same as if x1 would be the mean. I mean, those cases are like really same. And I won't be getting the equation for such. I mean, you can get that, right? So for half of a oscillation, what I can do is I can show you how the force varies. Like from when the particle is from 0 to x naught, you can see, you can check that this equation is followed, and you can actually say that uh, the amplitude for this oscillation will be x naught minus x1, and it will stop for the next time when it reaches uh, some x, which is x naught minus x away from this x1. So let me say it as what can I say, uh, uh, so let me do a quick calculation here. So x1 minus x naught plus x1. So yeah, it is 2x1 minus x naught. This can be a positive quantity or can be a negative quantity. For we can uh, I mean, create two cases, for one for which this is negative, and one for which this is positive. And if this is positive, then it will be on the positive x-axis and won't come to the negative x-axis, right? So yeah, half of our work is done. Now let us create two cases, one in which it is uh, positive, and one in which it is negative. So I will be explaining the positive part right here. So if it is positive, what does that mean? Um, if it is positive, then it will come to some place in between this, and it will stop there, because uh, in this region, I can just highlight that. So in this region, the friction force is actually more than the maximum spring force. So it will only just end its lifetime as an oscillating particle there, and it won't oscillate any further. So this is not the case that we're interested in. So I mean, we are interested in, but not for now. So this part is done. Now for the positive part. Sorry. The positive part is done. Now let us consider the negative part. Uh, Now, if it is negative, we can again rotate the rotate our whole axis about the y-axis 180 degree, uh, and then what we get is something like this. Yep, something like this. We will have our particle right here. Yep, and this will be our changed x-axis, and y-axis will be staying as it is. It doesn't really matter for the y-axis, because we're only rotating it about y-axis, so y-axis remains the same and x only changes. I mean, x only shifts from positive to negative and negative to positive. And now we can again do the same calculation as we did for the above case, in which we actually started from the positive x-axis, and we can do the same iterations. So basically, what uh, all this means is, when our particle is in between uh, x1 and minus x1, it won't oscillate any further. There is another distinction, x 2x1 minus 2x1, and when the particle, let me uh, let me color this, and then I will continue. Yeah, so I colored different portions of the graph by different color, and when our particle is in this purple region, it will go to the negative x-axis, and when it is in this purple region, it will go to the positive x-axis, and somewhere, not necessarily to the purple, I mean, not necessarily purple will go to purple, but somewhere. And when our particle is in the green regions, it will not traverse across the y-axis, rather it will only go from green to the immediate yellow region, and same for this case. So basically, that's it. Like, and when it is in the yellow portion, it will stay in that yellow portion, I mean the orange portion. So here it stays, here it jumps, and here it jumps once, I mean not across the axis, and here it jumps across the axis. Yep, across the axis. This is quite a significant thing, I think. So all in all, what we can say is, each chunk of half oscillation can be regarded as a different oscillation about a different mean, and switching them back and forth between two such specified means can give us the whole uh, trajectory of the particle. And in this case, the trajectory is especially easy because you can shift back and forth between this mean and this mean, and you can find the trajectory. And uh, the second point, the proof kind of thing that I want to talk about is, with this can also be shown mathematically. I mean, what I'm going to speak, if you write them mathematically, then you will be proving that. uh, Thing is, when the particle is moving towards the y-axis, or away I mean towards the y-axis from from positive x-axis, or away from the y-axis from on the negative x-axis, the direction of frictional force is always in this direction. So it is like displacing the whole half oscillation towards a point in positive x-axis. This is the same thing that happens when you hang a, a spring mass system uh, vertically, right? So now the mean position shifts from the actual mean when it is horizontal to somewhere below, and now this is the new mean. Exactly the same thing happens here. So when the particle is going in this direction, the frictional force is acting in this direction, therefore the mean shifts from here to here. And again, when the particle is moving in this direction and the friction force is acting in this direction, the mean shifts from this point to this point. That is actually the proof. And if you write it mathematically, x1 turns out to be f by k, and yeah, that's basically it. And now for the second part of this video, um, about the time part, but to say uh, this uh, oscillation is a special kind of oscillation because the force remains constant, uh, which leads to some change in mean, some definite change in mean, to say if force is definite, obviously, and therefore the time period actually only depends on k and m, the general case in SHM. So omega for each half oscillation can be regarded as something like root over of k by m, which is uh, from SHM. So, and when you see that, it does not depend on amplitude, right? So for every half oscillations that the particle performs about its mean, which is reassigned again and again, switching back and forth from this x1 to minus x1, uh, the time period stays the same for every half oscillation. Again, this points out to a very interesting fact that, and also we know that the particle has to stop when it reaches this uh, region, this region, I mean. So, and we also know that it will reach this region in after performing some multiple of half oscillations, right? Because we are not allowing for some uh, partial half oscillation, something like 1 by 4 of a oscillation or something like that about the reassigned means. So it will take integral multiple of t by 2, where t is the time period of a complete oscillation, uh, which follows complete oscillation of an SHM, which follows this I mean. Um, so it's kind of easy to write the number of oscillation, which is n into t by 2, where uh, t by 2 is actually uh, pi by root k root m. Yeah, so it is a new thing. Like if you have seen this uh, case, this oscillation kind of thing from first, um, you would not have like guessed that, I think, because you might be thinking that it can stop anywhere, like uh, time period of SHM, how can it matter here? But after doing it mathematically, we get that it is like n times pi root m by k, uh, which is in itself is nice. It's like great thing because it says that only such oscillations are allowed in this case, which uh, have their uh, lifetime as n into pi into root m by root k. Um, that is really nice, at least for me. I guess it should be for you too, because it came out of nowhere, right? Like I, it was really nice. In fact, it was like, yeah, it is like easy to find the uh, end points and the time it takes to uh, end the oscillations, that uh, we can actually show this by a code on computer, uh, that if you give initial uh, coordinate of the particle and set the initial time to be 0, then we can actually predict exactly where the particle will stop its motion and what time will it stop its motion, because time can be directly got by the number of half oscillations into pi into root n by root k. Let us actually do that. So this is the code that I have written for the situation, for the particular case of this kind of harmonic oscillation damped with frictional force, to say the frictional force is constant. So uh, I will be explaining the code like a in a sort to say. So count is equal to zero. This is something which will say like the count variable will say how many times this particular uh, loop has been run. So one so if it runs this chunk of code once, I mean this chunk of code once, uh, it will increase the value of count by one. Then if it runs again, then it will again increase the value of count by one. Let's keep that aside. So and F, K, X are the frictional force, which is a positive quantity in SI units, and K is the spring constant, and X is that's the start point, and these two are variables that we can assign. And the program will ask the uh, person doing that to assign values for F, K, and X, and then it will do this computation. So if you see this, this is the if I remember correctly, is the reason which was marked with purple, I guess, in the uh, XY code in the axis that I drew. I will be showing a picture right here, like right here. uh, I hope you saw this picture. So when it is in this condition that x is less than minus 2 f by k, and x is greater than 2 f by k, uh, I did this iteration, which is like uh, bring that x to, I mean, change that x, this value says that they change that x to the value uh, in negative. If it is in purple region, change the x to, I mean, move the particle, I mean, do half of the oscillation and change it from its initial position to final position after half of the oscillation. Yeah, so it did that, and I think I have explained this uh, point previously, where this is x1 and this is x1. So if you do if you simplify this here, you will get 2x1 minus x, which is what I wrote earlier. It is that only, and I have written x is equal to absolute x, I mean reassign x to be positive. This is because if x turns out to be negative, then I would have to write a lot of extra codes, which is not necessary, because that positive negative thing can be done with this count value. Yeah, so I have explained how count increases before. Now suppose that this code ran for like 3 times, then what does that mean? If it ran 3 times, means the particle has crossed the y-axis 3 times, which means it went from positive x-axis to negative x-axis, then again to positive, then again to negative, which means that if count is like like if the count is even, then it is in the positive x-axis, because 0 1 then again 0, I mean 0 1 then again 2. So if count is positive, it means it is on the positive x-axis, and if it is negative, then it is on the negative x-axis. And I have also included this point that x should not be equal to 0. This is because like if it is 0, then um, it is at the origin, right? So it is on x-axis and on y-axis, and saying that it is on positive x-axis or negative x-axis doesn't make any difference, and both are equally correct and equally wrong. So I won't be saying that. And in between this, there is another chunk of code, uh, which is for the, if I remember correctly, that middle portion. I will be modifying it, I mean what I mean around here by a photo. uh, yeah, so this shows that region. And and if x falls in this region, then it will obviously not cross the x, I mean the y-axis, as I have explained earlier. So if it is on the positive x-axis, it will stay on the positive x-axis, and if it is on the negative x-axis, it will stay on the negative x-axis. So I have not included count plus or minus 1 over here, because this does not affect if the final position is uh, positive x-axis or on the negative x-axis. Um, Also, this code is written specifically for positive x inputs only. So this condition actually did not make any sense, but um, anyways, leave that aside. Here is count one, and we can also include another variable which may be like say y. We can initialize y to be 0, and then say that, I mean, here we can say that y is equal to count. And yeah, so again we can write just below this x code that I mean, in with an indentation that y plus equal to 1, which will increase the y value by 1. So y will become count plus 1, and that will happen only if x comes to this region, right? If it does not come, then it won't happen. And finally we can also print um, the time that it took. So we can, after this print statement or anywhere, I mean, before this if statement or else after this print statement, we can write uh, print then the value of y into uh, pi into root m by root k, which will actually give the time for the after which the particle will come to rest. Um, that is actually nice. You can actually do that. Uh,
Yeah. You don't need to see. Yeah. So I will be running for two types of variable, two cases, and uh, will be showing that what is the downfall of kind of assignment that Python does. Not downfall, like you can negate that, but like it saves numbers not by uh, the exact number. I mean, if you type 2 by 3, it does not save it for like 2 by 3, rather it saves it as 0.6666 dot till a finite number of digits. And this will actually create a problem right now. Like if I run the code, which I guess will run, there's no reason why. Yeah, okay. So I give the value of the frictional force to be 4. I give the spring constant a value 2 on inside. And I have assigned the start value to be 57, and the endpoint is 1 1, and it is on the positive x axis. Nice. Great. Uh, which should be true. Like you can check this and it will come out to be true. I will check that too. Uh, you can if you want. And the problem part now is to talk about. Suppose that I give the friction value as 2, positive 21st string constant as 3, start point as 4. If you do the calculation, you should get 0, but here I am getting 6.6666, then to the power minus 16. This does not make any sense, and it should not, because if you do this logical calculations manually, you will get 0, exact 0 to say, but uh, due to this saving mechanism, code gives some wrong thing. And I don't know what this error is called, but I think it is static semantic error. Not this. So that's it. This